Hello, you are welcome to today's class. We will be having our lecture on Chem 307, and today we'll be treating Unit 3. Unit 3 is on molecular orbitals of molecules. Uh, the In chemistry, a molecular orbital are usually constructed by combining atomic orbitals or hybrid orbitals from each atom of a molecule, specifically the electronic configuration of a molecule, mostly molecular orbitals, which is represented as a linear combination of atomic orbitals. The slide before you is a definition. Molecular orbital is a mathematical function describing the location and wave-like behavior of an electron in a molecule. They are usually constructed by combining atomic orbitals or hybrid orbitals from each atom of the molecule or other molecular atoms from groups of atoms. Now, in the combination, you have linear combination of atomic orbitals. That's LCAO. You use the molecular orbital method. They provide a simple model of bonding in molecules, which is better understood through the molecular orbital theory. Most methods, particularly in computational chemistry today, start by calculating the molecular orbitals of the system. And a molecular orbital describes the behavior of an electron in the electric field generated by the nuclei and some average distribution of other electrons. Now, in the case of two electrons occupying the same orbital, the polar exclusion principle demands that they have opposite spin, which is what we've discussed in our previous class. In the slide you have before you, we have the molecular orbital 1, which is the sum of the atomic orbitals of atom 1 plus the sum of plus atomic orbital of atom 2. Or if you look at them in maybe in terms of uh, two atoms or the same atom that is together, you have MO1, which is atomic orbitals of maybe A1 plus minus the atomic orbitals of A2 or atomic orbital of B. The molecular orbital craters are called linear combination of atomic orbitals, and molecular orbitals created from the sum and the difference of the two wave functions, that is the atomic orbitals. A molecular orbital must have many molecular orbitals as there are atomic orbitals that are actually present in the molecule. As there are atomic orbitals that are present in the molecule. Now, if we have the slide you see before you, or in other words, in chemistry, molecular orbital, which is a mathematical function that describes the wave-like behavior of an electron in a molecule. This function can be used to calculate chemical and physical properties, such as the probability of finding an electron in any specific region. In the first figure we have there, you see one S1 combining with another S1. The resultant product is that there is a constructive interface, the two of them that are combined together. Like you have 2, 0, 0, or you have 2x brought together to touch each other. There's an interface between them. Now, the bonding probability density is what you see probably in B. B shows how the two of them, or maybe the two X are now mixed together, or the orbitals are now combined together. They gave you the chart you see in B, that is bonding probability density. The next is what you have the C. In C, you have one S and another one S, which is negative. In the earlier case, we presented the two SS are positive. Now in the lower one, one is positive and one is negative. That is the wave functions that are combined together. Now, after the combination, you see a construction similar to what we had earlier in the two hydrogen atoms. Here also, they are actually bound together. They have been mixed together. And you will see the chart or that is plotted. One goes up, one goes down. The peak of one is down, the peak of the other is positive. Unlike the earlier one that we have, both of them have their peaks which are positive. But the later one that we have, which is the combining of one positive and one negative, gives you a peak that is positive and a peak that is negative. The resultant product is that there is an antibonding probability density. That means it's as if no bond is actually formed between the two atoms. If you see the two of them are distinct atoms, or you have the two X, which are brought closer, but they are not linked, they are not touching each other. In other words, there is no bond that is formed between the two of them. A graphic example, if we look at the next figure, that is of the hydrogen atom, you see the arrow going up, that is the energy of the orbital. You have the atomic orbitals, one on the left side and one on the right side. Now, the atomic orbitals, below it is the bonding molecular orbital, and above it is the anti-bonding molecular orbital. You will see that if you go back to figure 1, the figure we have below is as a replica of figure 1. The resultant product of combining one S with one S, that is one hydrogen atom plus another hydrogen atom, to give you a bond existing between two hydrogen atoms, which what you see in B, that is the bonding probability density. In the second one, you have one bonding atom and one anti-bonding atom, and the resultant product is what you are seeing in D, the anti-bonding probability. The two atoms or electrons are not bound together. Now, those two resultant products is what you see in the molecular orbital structure that is presented in slide 5. You will see the bonding molecular orbital below. In above is the anti-bonding molecular orbital, while in between the two is the atomic orbitals. The atomic orbitals combine to give you the molecular orbital. Now, the construction you have is the molecular orbital structure of a hydrogen molecule. One hydrogen atom donates an electron to the bonding molecular orbital, and another hydrogen atom donates an electron to the bonding molecular orbital, making two electrons combining together to form one bond, which can be seen or as illustrated in the figure that you see before. Now, if you look at the bond order, or let's look at the explanation of the formation. Now, in the A that we have in our earlier in slide 4, the A is a formation of bonding sigma 1s molecular orbital for hydrogen as the sum of wave functions of two hydrogen 1s atomic orbitals. Now, in the B part of it, that is a plot of the square of the wave functions for bonding sigma 1s molecular orbital. This illustrates increase in electron probability density between the two hydrogen nuclei that are brought together. Now, in chart C, which you can also see in the slide before you, it shows the formation of an antibonding sigma 1s molecular orbital for hydrogen as the difference of the wave function of two hydrogen sigma 1s orbitals. And the D, the resultant product, that is the one you see in plot D, is a plot of the square of the wave functions for the sigma star 1s, that is the antibonding molecular orbital, which illustrates the node corresponding to 0 electron density between the two hydrogen atoms. That means there was no bond that is actually formed. Now, if we look at the two, we try to look at the bond order. The bond order is the number of bonding electrons minus the number of antibonding electrons divided by 2. The number of bonding electrons minus the number of antibonding electrons divided by 2. In other words, you can also define bond order as the number of paired electrons in the bonding molecular orbital minus the number of paired electrons in the anti-bonding molecular orbital. If we go back to slide 5, which we showed earlier, we discovered that the bonding molecular orbital, which is sigma 1s, has 2 electrons, while the anti-bonding molecular orbital, sigma star 1s, does not have any electron. So if you use our first definition of bond order, number of electrons in bonding molecular orbital minus number of electrons in the antibonding molecular orbital divide by 2. That is going to give you 2 minus 0 divide by 2. And that will result to 2 over 2, which is 1. That's why you have one bond that is existing between two hydrogen atoms. If you use the second definition in terms of paired electrons, that means you have one paired electrons in the bonding molecular orbital, and there is no electron in the antibonding molecular orbital, which means the bond order is 1 minus 0, which is equal to 1. That still shows us why hydrogen molecule has one bond that is actually keeping the atoms together. Sorry. One atom that has the atoms, one bond that keeps the two atoms together. If you look at the diagrams we have before us, it's like what we had earlier in the earlier diagram that we have there is a diagram of the molecular orbital of molecules. So you have the increasing energy in terms of you have the bonding molecular orbital below, you have the anti-bonding molecular orbital above, and you have the atomic orbitals in between them. Now for a molecule of hydrogen plus, H2 plus. H2 plus means there is only one electron that is present in the molecule. So therefore there is only one electron, and that's why you are seeing only one electron in that construction. In the B construction, which has to do with helium plus is He2 plus, and you have 2 electrons in the bonding molecular orbitals and 1 electron in the anti-bonding molecular orbital. That's why it's actually carrying the positive charge, because of the single electrons or the unpaired electron in the anti-bonding molecular orbital. And in the third, that is the C, is about He2. He2, that is helium itself, has 2 electrons in the bonding molecular orbitals and also have 2 electrons in the anti-bonding molecular orbital. If we apply the bond order principle, that is 2 minus 2, that is 2 minus 2 divided by 2. 2 minus 2 is 0. 0 divided by 2 is 0. That's why helium does not exist as a diatomic molecule. There is no bond that exists between 2 helium atoms. If we try to use the paired electrons method in defining it, that is 1 minus 1, and 1 minus 1 is 0. So helium does not exist as a diatomic molecule. Once again, the Once again, as said earlier, the molecular orbital energy level diagram for hydrogen shows an increase as the energy is progressing and going up. The two available electrons, one from each hydrogen atom in the diagram, is filling the bonding sigma 1s molecular orbital, because the energy of the sigma 1s molecular orbital is lower than that of the two hydrogen atomic 1s atomic orbitals. The hydrogen molecule is more stable at a lower energy than the isolated hydrogen atom. So hydrogen will prefer to exist actually in a di-molecular state because it is more stable. A body molecular orbital is always lower in energy, that is more stable, than the component atomic orbitals, whereas an antibonding molecular orbital is always higher in energy or less stable than the corresponding atomic orbital, than the corresponding atomic orbital. If we go back to our slide, if we go back to the slide in the in slide number 10, you will also observe there how electronic configuration is written in terms of the orbitals: 1s, 1s, 2s, 2p, 3s, 3p, 3d, and so on. So let's take this exercise briefly as we are having it there. Write the expanded and shortened ground state electronic configuration for chlorine. Write the expanded and shortened ground state electronic configuration of chlorine. Chlorine has an atomic number of 17. So the expanded electronic configuration is going to give you 1s2, 2s2, 2p6, 3s2, and 3p6. If you add all the subscript figures, that is going to give you 17. Now, the shorthand form is to look at the nearest inert gas configuration. The nearest inert gas configuration. So the nearest inert gas configuration here is neon. So you put neon in bracket, then you write the outer electronic configuration, 3s2 and 3p5. 3s2 and 3p5. So the first is the expanded form. You write all of them together. The second is the shorthand form. You write the nearest noble gas or inert gas, then the outer configuration. If we also try that in terms of chromium, the expanded form is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5. While the nearest noble gas or inert gas is argon. So if you have to write the shorthand method, is argon in bracket, you have 4s1 and 3d5. I'm sure some of you will try to ask the question, why not 4s2 and 3d4? The reason is that there is stability in half-fill orbitals, stability in half-fill orbital. So by half-fill here, that is the 3d5. The d orbital, by having 5 electrons, is more stable. So the electrons, instead of having 4s2 and 3d4, would prefer to move to the d. So you have 4s1 and 3d5. 4s1 and 3d5. 4s1 and 3d5. Once more, if I try to take us back to what we have tried to look at in this class, we try to define molecular orbital as a mathematical function that describe the location or wave-like behavior of an electron in a molecule, or find the probability of finding an electrons in a molecule. And they are usually constructed in terms of combining atomic orbitals or hybrid orbitals to actually give you a molecular orbital. So if you have two hydrogen atomic orbitals coming together, they will give you a molecular orbital. It's like what you have in this slide, in this third slide that we have before us there. You have for MO1 is equal to AOA1 atom 1 plus AO atom 2. Or the second one, MO1 is equal to AO atom A minus AO atom B. That is atomic orbital of atom B. The molecular orbital created is so-called linear combination of atomic orbitals. They come together to give you a molecular orbital. Now, on slide 5 tries to give you the more structure of what actually we are talking about. A is about the wave function of the two 1s, 1s coming together to give you a bonded probability density. I gave you an illustration in terms of an egg. You have one egg and the second egg. You bring them together. The two eggs edges are touching each other. But when you try to break them, you mix them together. It forms something like a ball. It's a mixture. So the probability of finding an electron in such a situation is very, very high. And so all the particles in the two ends are now mixed up together and they are bonded together. So in this case, the two hydrogen atoms are linked together in the molecule to give you a hydrogen bond. The second example you have there is in C. That is wave functions combined of the two, 1s and a negative 1s. The 1x positive and the 1x negative cannot be able to bound together. In the transition state, you see one has the peak positive, the other one, the peak is negative, and they are almost equal. So they cancel each other. If you see, you go to D, you discover that in between the two, there is anti-probability of electron density. You will not be able to find electrons within that area. So there is no bond that is actually formed. The slide 5 is actually an illustration of a simple construction of the molecular orbital of hydrogen. So you see hydrogen with one electron coming from one atomic orbital, another electron coming from the other atomic orbital. They combine together to give you one molecular orbital, while the antibonding doesn't have any electron there at all. Hence, the hydrogen atom prefers to exist in a molecular form with a bond that binds the two atoms together. The next we see is what we try to see the same description of all what we are actually having up there. So once more, I want to thank us for participating in this class. Thank you very much.